Okay, so having studied the uh, population and sample regression functions, now it's our turn to estimate the unknown parameters and then see whether those parameters come out to be significant or not. Now, when I'm talking about unknown parameters, there is more to it than what we actually see. We may think that the unknowns are just two such quantities or two such parameters in the equation, but as I said, there is more to it than what we actually see. So how do we estimate? So we we use the method of least squares here, and later on we'll see that there's a very famous theorem which will justify our usage of this method, uh, and this gives us the best estimates, of course. So what is the method of least squares? The method of least squares is basically minimizing the residual sum of squares. So I've written the residual sum of squares on the screen. So that's your residual sum of squares. So method of least squares aims at minimizing this. And how do I minimize this? Simple mathematics. I simply differentiate the residual sum of squares with respect to the two unknown quantities in the equation, which is b0 and b1. This is what we are interested in finding out. So there would be equations, and then solving those equations, these are the estimators that I get, the b0, the b1, right? And of course we can obtain ei, which is the actual values of yi minus the estimated values, and these. So as I said, there is more to it than what is in appearance. We thought that the only things unknown were beta naught and beta 1, but then we have four unknowns in the equation: beta naught, beta 1, the error term ui, and the variance of the error term sigma square. So these are the four estimators. The first two estimators are obtained by the method of least squares. Now, how do we physically interpret these estimators? So if we look at the equation, y is equal to beta naught plus beta 1 x, if I simply put x is equal to 0, the value of y becomes your beta naught. So if the sample values of the explanatory variable, right? Okay, I'll come to this later on. So, and then b1 is nothing but marginal change in y with respect to change in x, or I would say rate of change in y with respect to unit change in x. So if x changes from x to x plus 1, let's say x was 10 units and it has now moved on to become 11 units, then y, which would have been some y units, would now be increasing or decreasing by b1 units depending on the sign. So as x changes from x to x plus 1, y would change from y to y plus b1. Now we have to note here, when I'm saying that b0 is the value of y when x is equal to 0, we have to note that if the sample values of explanatory variables are a long way away from 0, right, they are nowhere near 0, then extrapolating the regression line back to 0 may be dangerous, because x is equal to 0 is not a part of the data set. So therefore extrapolating this line back to 0 may be very, very dangerous, and then a literal interpretation will lead to nonsensical conclusions. As an example, let's talk about the data that we had seen before, the CT severity score and age. They appear to be correlated. So I believe that such a regression function would hold good. CT severity score can be determined by age, right? So B naught, as per the above interpretation, is nothing but the CT severity score when age is equal to 0. So literally, we cannot have a situation where age is equal to 0, right? If age is equal to 0, age is equal to 0, then the person doesn't exist. So I am forcibly extrapolating the regression line to pass through the origin, right? To pass through the value x is equal to 0. But can age be 0? No, it cannot be. So therefore, it will lead to nonsensical kind of conclusion. So the value of y when x is equal to 0 should also be thought of with a word of caution, that extrapolation outside the data sets is not possible. And another thing to note is that the b0 and b1 are simply estimates of beta naught and beta 1, and hence interpretation is really on an estimate only. Interpretation is not on beta naught and beta 1. Interpretation is on the estimate of beta naught and beta 1. And the regression equation here refers only to the general tendency for a sample. So these beta naught and beta 1 are tendency of the relationships to exist for a specific sample taken by me. If somebody else comes and takes a sample, then for them B naught and B1 may be slightly different, and so therefore their estimates or their interpretation is for their particular sample only. And finally, interpretation of all these terms is conditional on the equation being correctly specified. So if this is the equation I am looking at, Ct is equal to B naught plus B1 H, then I am assuming that such an equation is correctly specified. There is no misrepresentation of the functional form, and therefore the interpretation is conditional on that. When we talk about estimates, we often refer to the standard errors of the estimate to see how good such estimates are. So these are the standard errors. The Gauss-Markov theorem, as I stated before, it says that the estimators obtained by the method of least squares are blue, the best estimators. So they, in the class of the linear unbiased estimators, that means in the class of all the easiest possible unbiased estimators, the least square estimators are the best. That means they are the most efficient kind of estimators. We are not expecting you to remember any formula. These are just for the taking note of. That's it. Then another associated statistic is the goodness of statistics. In fact, whenever we run a regression, the first thing that we look at is the goodness of it. To see whether the model is fitting appropriately to the data and whether it is giving considerably better fit so that the model is worth taking forward all the analysis. So there is obviously bound to be variation in yi because it's a sample data. The observations are bound to differ from one another. So the variation in yi is now split up into two parts. One is the explained variation, that means the variation which is being explained by xi, and the unexplained variation, the variation which is not being explained by xi, that means which is being explained by the error term. So r square is nothing but the proportion of explained variation. So obviously the limits of r square are between 0 and 1. R square would be 1 when everything is explained, nothing is unexplained, right? So the variable x is explaining every variation. So r square is equal to 1. When everything is unexplained, when there is nothing explained, then r square is equal to 0. So in a nutshell, we would want to have the values of r square closer to 1 so that the model is good. R square in the vicinity of 0 is not a good thing. R square in the vicinity or far away from 0 is considered to be good. In fact, whenever tomorrow if somebody comes and says what is the proportion that your model is explaining, so the first thing we look at is r square. So if r square is equal to, let's say, 0.738, then 73.8% variation in yi is being explained by my model. Model means the x variable. And then for a simple regression model, the last equality also holds, that the r square value is nothing but square of the correlation coefficient. And that is why we started off with correlation coefficient, because until and unless correlation exists between variables, there is no point in doing regression. If the correlation is 0, then the regression is obviously 0. If the correlation is different from 0, then the regression becomes meaningful. Now, many of the names are given to this r square. Some people call it as the coefficient of determination as well, or we call it as a goodness of fit statistic. So, but then both of them, of course, refer to your r square value. Now, the most important part of your regression analysis. So, whatsoever estimators, whatsoever B naught, B1, sigma square, R square that we are deriving, we wish to know whether these values are significant enough to consider the model worthwhile. So, these are the following test statistics. So, the order is, of course, exactly the same in which they are given. This is how we go about testing. The first thing, whenever we run a regression, after noting down the values of B0, B1 and their standard errors, the first thing we do is to see whether the R square that I'm getting, let's say I'm getting R square is equal to 0.234. So that means 0.4% variation in Y is being explained by X. So should I consider this R square value to be equal to 0, or should I consider it to be different from 0? So equal to 0 indicates that my model is bad. I should stop the process here itself. And greater than 0 means that yes, my model is decent enough. I can go on with further analysis of this model. So R square is equal to 0 versus R square greater than 0. The test statistic is this. And the name of the test is F-test, or more popularly known as ANOVA. So once we know that the hypothesis of R square is equal to 0 has been rejected, that means the model is worthwhile for consideration, we start on with the next checking the significance of the regression parameters. Now the t-test allows us to not only check for the significance of parameters, but also to see whether these parameters are equal to any pre-existing or any known value. Known value means the value derived from any previous analysis. So the general setup of a t-test is this. So if I put c is equal to 0, I am basically testing whether beta naught is equal to 0 against beta naught not equal to 0. So that's the test, and the name of the test is the t-test. We also call it as the t-test for marginal contribution of explanative variables, or we call it as the t-test on regression coefficients. Same way with beta 1, I can test whether the contribution of x on y, the marginal change of y with respect to changes in x, is it significant enough? So I just put c is equal to 0 here, and I use the t-test to basically develop a test. Now the second and third concepts, when c is equal to 0, they basically allow us to check whether intercept is at all needed in the model. Secondly, whether the slope is significant enough to consider this model for further use. So in fact, in a way, the first and third hypotheses are exactly same. So if b1 is equal to 0, that means x has no impact on y, ideally meaning that r square is also 0, because x is not explaining any variation in y. So for now, for a simple regression model, the third test here and the first test here are similar. They will be giving you same kind of conclusions. However, the advantage with the third test is that I can check for any other value of c different from 0. So that will basically see whether my research or my data corresponds with the research which has already been done on this topic earlier by somebody else. The fourth test is, of course, if the variation sigma square is equal to c or not, to test whether this variation is c or not. So this is the chi-square test. The fourth test is something which we which we don't use very often. Right? Now, when we talk about estimation, there are two different ways in which you can provide estimate. So the unknown parameters earlier were b naught, beta 1, sigma square, and the error term ui. So the earlier estimates that we provided were the point estimates. Now suppose somebody asks a question to you, what is the average CT severity score of Delhi population? So one person may respond with a single number. Let's say somebody says that, okay, the average CT score is, let's say 2.2 or 3, right? The average CT score is 3. And somebody else may be a little more cautious, and then they would respond by saying that the CT score lies between, let's say, 1 and 4, right? So the person who is saying 2 is giving you a point estimate. 1 point is giving is an estimate for the question that you have asked, and the other person who is saying 1 to 4 is giving a kind of interval. So the earlier formulae that we saw were for the point estimate. This is the interval estimate for beta naught. So beta naught lies between these limits, beta 1 lies between these limits, and sigma square lies between these limits. So these are your point estimates. Then finally, the purpose of regression is not only to evaluate the impact of x variable on your y variable, it is also to predict. So for regression equation, if I have any value x is equal to x naught, then the predicted value of y from the equation is obtained by this. So that's your point predictor. And if we don't want a point, if we want the predictor to be an interval, some lower limit and upper limit of the interval, so that's the lower and upper limit of the interval. These are the formulae. So all these things are easily readily available on software. So the formulae may not be remembered. You can just make a note of these formulae. You don't need to actually remember.